Hello and welcome all of you for my third class, that is on module 1, simple stresses and strains related to the strength of materials. In the first class we tried to build some concepts with respect to stress, strain, modulus of elasticity. Then coming to strain, we started talking about lateral strains, longitudinal strain, then the Poisson's ratio. And once we know the Poisson's ratio and other things, we will be able to establish or work out various types of problems. And then we also introduced the concept of what is called allowable working stress or the factor of safety approach. Then the factor of safety was defined as the yield stress or the proof stress divided by the allowable working stress. Then the concept of lateral strains and Poisson's ratio, and we were able to establish a relationship between lateral strain is equal to Poisson's ratio times the stress divided by the modulus of elasticity, and usually it is found to be in the range of 0.25 to 0.33. Then we tried this particular example one wherein the bar of sectional rectangular bar with some dimensions forces, then we determine the changes both in the longitudinal direction as well as in the lateral directions, like we determined the decrease in length, increase in breadth, increase in depth. Then the second problem was slightly different to the first one, wherein we had bars in 3 discrete segments with varying lengths, with varying geometric dimensions, like this is circular, this is square, subjected to only end forces of 20 kilonewtons. I told you that whenever you are solving problems of this kind, first and foremost thing that you have to ensure is to study the equilibrium. Now directly the forces are balancing each other, so it is in equilibrium. Hence we concentrate on portion A, portion B, portion C separately with the set of forces being applied, and then we find out stress in each portion, then we will find out the change in length in each portion. And because in this particular case every portion was subjected to elongation, we could simply add without any algebraic signs. Well, in the third problem that we studied in the last class, here bar is continuously changing, a stepped bar, of course progressively decreasing 10 mm, 14 mm, 20 mm. The end forces were there. In addition, there were internal forces. The magnitude of P was not given in the problem. So first what we need to do, it is in each portion you need to study the equilibrium of this. So for the equilibrium of the bar, we try to determine what is the force P, and we found it as 20,000 newtons. Then we constructed the free body diagrams for each portion. Then each portion was analyzed separately with respect to sectional areas, then change in length in the portion of the bar, change in length in portion 2, and change in length in portion 3. In all the cases, we found that the bar each portion was subjected to compression, so there was a decrease in length. So without any algebraic signs, we were able to add all the changes, and we were able to get the total decrease in length as 0.857. With a note that it may so happen that in some problems, some portion of the bar may be subjected to tension and some may be subjected to compression, which will result in either increase or decrease in length. In such cases, you need to add, to determine the total change in length, you need to add them with proper algebraic signs. So generally we use positive sign for increase and negative sign for decrease in length. This was a very interesting derivation we did, that is elongation of tapering bars of circular cross section. The problem is that here the diameter is continuously changing. It is not constant, so it is continuously changing. Then in that particular case, you cannot divide it into any discrete number of segments. So how do we solve such problems? We solve such problems by considering an elementary strip. At this we will call this as the diameter D, and we will try to establish the equation for D in terms of D1, D2, L and X. So with this we were able to derive this particular equation. Then we determine what is the cross-sectional area at that point. Once you know the cross-sectional area, you can find out the stress. Once you know the stress, you can find out the change in length over that elementary length. If you want the total change in length, we integrate them. So the process of integration is slightly involved, not complicated, slightly involved. So try to practice this. Next, we substitute the limits and we try to bring in various simplifications at various stages, and finally we were able to derive this particular equation. 4PL divided by pi e d1 d2, and in the last class towards the end I was mentioning that how do you say that this equation is correct? By a simple consideration that if d1 equal to d2 means if it were to be of constant cross section, say d1 equal to d2, we will say it is equal to the diameter d, then it will be equal to pi d squared. So pi d squared divided by 4 will give me the area. So delta L is equal to PL divided by AE. So this is what we studied till now. Now let us continue this. Let us try to solve this problem. Example 4. A bar uniformly tapers from a diameter 20 mm at one end to diameter 10 mm at the other end over an axial length of 300 mm. So this is d1 and this is d2 and the length is 300 mm. This is subjected to an axial compressive load of 7.5 kilonewtons. If E is equal to 100 kilonewton per mm squared, determine the maximum and minimum axial stresses in the bar and the total change in length of the bar. This is a simple example. So this is the data that is given. As I have told you, when you are solving problems in strength of materials, be very careful with respect to the units. Initially, whatever units that is given in the problem, try to convert them into a consistent system of units. So wherever newtons is there, wherever the newton appears, you put everything in newtons and put everything in mm, so that you will not go wrong in any unit conversions. So minimum compressive stress occurs at d2. Why? Because the diameter is maximum there, as the sectional area is maximum. So we will find out area at d2. Once we know the area at d2, we will find out the minimum compressive stress as 7500 divided by this. I will be having 23.87 MPa. Then maximum compressive stress will occur at d1 because the sectional area is minimum there. So we will find out area at d1 and we will find out sigma minimum, which is about 95.5 MPa. Now the total decrease in length, we have this formula 4PL divided by pi e d1 d2. You can substitute these quantities, all those values, and you will be getting this value as 0.143 mm. You can directly use this particular equation, or otherwise if you want you can solve the problem from fundamentals itself. You know d1, you know d2, wherever in the derivation we have done, wherever the d1 d2 were there, you start putting 20 and then 10 mm, 10 for this and then 20 for this, and you can finally work it out. By the process of integration also you will be getting the same result. Okay, now let us go in for a different type of a problem, what is called elongation of tapering bars of rectangular cross section. Previously it was a circular bar, tapering bar but circular. This is a tapering bar of rectangular cross section as shown in the figure. The length is L. The width at this end, minimum width, we will call it as B. The maximum width, we will call it as capital B. T is the thickness. The thickness is constant throughout. Only what is changing? The width is changing. Width changes from lowercase b to uppercase B over a length L. Next, again as usual, like what we did in the previous case, we will consider a section S. We will consider an elementary portion like this. The width is dx and let the width at this particular point be equal to bx. Bx refers to width at any section x. That means when x is equal to 0, bx will be equal to b. When x is equal to L, bx would be equal to b. In between it will have values varying between b to b. Like we established equation for the diameter at any section, we can also establish an equation for the width at any section x using the principle of similar triangles. So in the same way, bx would be, I can write it as b, that is, this is the constant width which will be there throughout. Next, b minus b divided by L. How do we do it? We take this width, deduct this width, this change b minus this plus this, b minus b is there over a length L. You want it for x. So it is b plus b minus b by L into x. This again I will put it as k, where k is equal to b minus b by L. This derivation is very similar to the previous one, except that when you go into the process of integration, it will be slightly different. Otherwise, procedure wise, it is identical. So that means if you know the previous problem, this you must be in a position to do it by yourself. Anyway, let us quickly summarize this. Cross-sectional area of the bar at x. Area, it is a rectangular bar, so it is bx. Thickness t is constant. which we write it as b plus kx into t, because bx we wrote it as b plus kx. So I will be writing it as area of the bar as bx into t, which is equal to b plus kx into t. Once I know the area of the bar, I will find out the axial stress in the bar. Sigma x is equal to p divided by x, which is equal to p divided by b plus kx times t. Then change in length over dx, which we will call it as delta dx. Once you know the stress, once you know the length over which you want to find out stress, into length over which you are finding out the change, divided by the modulus of elasticity. Putting these expressions into this, I will be getting an expression for delta dx like this: p dx divided by et into b plus kx. Now, as usual, total change in length, we integrate it over the entire length 0 to L. Now, previously it was x to the power of n, now there is no x to the power of n. So, therefore, it is b plus kx. It is something like integral of 1 over x dx is log x. So, what we will be doing it is p divided by et. Remember, this k is there. So, through the process of integration that k comes out. Next, logarithm of b plus kx of 0 to L. This is a natural logarithm. So, I substitute the limits. So, p divided by et k, for x I will put it as L. So, it is logarithm of b plus kl. Next, this goes as 0. So, it is logarithm of b, which but we know that b plus kl is equal to b plus b minus b by L into A, which is equal to the capital B, very exactly similar to what we did with circular cross section, but only thing is some changes will be there with respect to cross sectional area, with respect to finding out the integrations and other things. So, with this substitution we end up with an equation like p is divided by etk log b minus log b, or which you can write it as logarithm of b divided by b. So, substituting again k is equal to whatever this, we finally end up with an equation like this: delta L is equal to PL divided by ET into b minus b into logarithm of b divided by b. So, the process of deriving expressions for elongation in the case of tapering bars, whether they are circular in cross section or rectangular in cross section, procedure is exactly similar. But only thing is some changes will be there with respect to the mathematics that is going to be introduced because of the change in geometry. So, in the previous case we used to get it simply as we got this equation, k is equal this one, delta L is equal to 4 PL divided by pi E d1 d2, whereas in this particular case we will be getting this equation as delta L is equal to PL divided by ET into b minus b into logarithm of b divided by b. So, this is what we are going to have for the expression for delta L. Yes. Let us try to solve this particular example based on these things. An aluminum flat, this is example 5, an aluminum flat of a thickness of 8 mm and an axial length of 500 mm has a width of 15 mm tapering to 25 mm over the total length. It is subjected to an axial compressive force P, so that the total change in length of the flat does not exceed 0.25 mm. What is the magnitude of P? If E is equal to 60,000 Newton per mm squared for aluminium. I will read the problem again. An aluminium flat of thickness 8 mm, T is equal to 8 mm, and an axial length of 500 mm, L is equal to 500, has a width of 15 mm tapering to 25 mm. So, smaller one I will take it as lowercase b, which is 15, that tapering to 25 mm, capital B I will take it as 25. It is subjected to an axial compressive force, means the magnitude of the force is not given. They say that it is an axial compressive force, but they have given that the total change in length of the flat should not exceed 0.25 mm, means delta L value is given. If that is the case, you are expected to find what should be the magnitude of load P such that delta L for this bar does not go beyond 0.25 mm. Just change in our equations. So, we are trying to recast that particular equation, whatever we have got. Instead of, we want to find out P. So, it is delta L into E T into B minus B divided by L logarithm of B by B. So, that is what I am going to put it here. I will substitute all these quantities, whatever we have, if you use these relations, you will get the value of P as 5.246 kilonewtons. Remember, you are evaluating the natural logarithm here. Well, instead of using the formula, this problem can be solved from first principles also, as indicated in the derivation. Instead of putting them as B and B, you can put these values, and finally at the end of the integration process, right, you could be getting this particular value of P as equal to 5.246 kilonewtons. So we have covered two types. One is extension of a circular bar subjected to a tensile load, next extension of a rectangular bar subjected to a tensile load. See, in both the cases, if you see, the self height of the bar is not included, because the self height of the bar will be acting vertically downwards. This does not contribute to any elongation in this direction. Therefore, the self height of the bar is neglected. Even in the previous case also, circular bar also, the self height which was acting vertically downwards was neglected, because that was never going to contribute to any extension in this particular direction. Or what we can say is that we have ignored the self height. Now let us go to a case where you cannot ignore them. Look here, this is elongation in a bar due to self height. Instead of having the bar horizontal and applying tension at the ends, suppose the bar is suspended vertically, right, maybe from a roof. A bar is suspended vertically. The cross-sectional area, circular cross-sectional area is A, length is L. Now I will be considering a section YY at a distance y from the bottom, and let me have the elementary width as equal to dy. Now in this particular case, what is happening? The weight of the bar is acting vertically downwards. So because of the weight itself, there would be elongation that is going to take place. So in the previous cases, we had ignored the self height based on the condition that self height was not directly contributing to the elongation. We felt that the elongation is taking place mainly because of the force that is being applied. Well, in this particular case, that external force is not there, but the elongation of the bar can take place because of the self height. In such scenario, how to find out the elongation is the question. Again, we will proceed like this. Let the weight density of the bar is rho. That is, we can put it as rho Newton per cubic, that is mm cube. Now consider a section YY at a distance y from the lower end. Weight of the portion of the bar, whatever you are considering, this is my section. So the stress at this particular point will be because of the weight that is coming below that particular section. So as a result of which, I will find out only weight of the portion of the bar below YY. Means unit weight, that is rho, multiplied by the cross sectional area, that is A, multiplied by this distance y. So that this gives me the volume multiplied by unit weight will give me the weight of the portion. This weight of the bar, right, contributes to the stress at this particular point. Suppose y, if you decrease it, this value will decrease, then the stress will also decrease. In the limit, at this particular point when y is equal to 0, the weight of the bar would be equal to 0, therefore the stress is also equal to 0. Likewise, if I go towards the top, you will have the entire weight of the bar that is acting, therefore the stress would be maximum at this particular point. Now we will find out stress at YY. Stress at YY is sigma y, which is equal to what is the force that it is acting? Rho AY is the weight divided by the cross sectional area. So stress at YY is equal to rho y, which I just told you. When y is equal to 0, stress would be equal to 0. When y is equal to L, the stress would be equal to rho L, and it varies linearly, which I will conclude it in the end. Now strain at YY. Once you know the stress, just divided by the modulus of elasticity. See how nice that Hooke's law is. We can solve number of problems based on that simple relation that stress is proportional to strain, or stress divided by strain is a constant quantity, which is called the modulus of elasticity, which we will determine it by performing a tension test for a ferrous material, for non-ferrous material. For example, like concrete, we perform compression test and we find out the modulus of elasticity. So strain at YY would be equal to epsilon y, which is equal to rho y divided by E. Then change in length over dy, which I will call it as delta dy. So, this is nothing but the stress is rho y, the length is dy divided by E. So, how do you find the change in length? Stress multiplied by the length over which you want divided by the modulus of elasticity. So, it is rho y is the stress, dy is the length over which you are finding out the change in length divided by the modulus of elasticity. So, the total change in length means integrated, integral of 0 to L rho y dy. So, if you perform the integration, it is a easier integration when compared to the previous two integrations. You will have rho y square divided by 2u integral 0 to L, or simply put it, you will get rho L square divided by 2e. So, now what I will try to do it is just to put this equation in a better form, or in a form which is very easily you can use them. I will multiply and divide this equation by a. So, next this L squared I will write it as L into L. So, what I will be doing it is rho a L means L squared, I will split it. Now, I am multiplying it by a, I will again divide it by a. So, you will have 2ae. So, that delta L does not change. Now, we know that rho a L is the total weight of the bar. So, I will replace this by capital W, which is the total weight of the bar. So, then you will have WL divided by 2ae. So, instead of this particular equation, this equation is more elegant, more simple for calculations. So, if you know the weight of the bar, you know the length of the bar, you know the cross sectional area, you know the modulus of elasticity, straight away using this particular equation you can determine the change in length, that is delta L. So, W is equal to rho a L represents the total weight of the bar. As I told you, the stress in the bar gradually increases linearly from 0 at bottom to a value rho L at the top. See, so far what we used to do it was the stress within a segment used to remain a constant quantity. Because of the sulfate, what is happening? Stress at any section you are going to consider, it is going to be different. It varies from 0 here to a value of rho L at this particular point. So, this is the fundamental difference between the applied load and the sulfate. Suppose the same bar, if we had applied, put it like this, and then we had applied tension throughout, it would have been constant quantity. Whereas, if it is suspended vertically, in addition to suppose, and if we had applied any force like this, you would have had one more diagram called P by A. So, here the stress would be equal to P by A, here the stress would be equal to P by A plus rho divided by L. That means, sulfate of the bar, right, influences the stress in the bar at various sections. Now, let us go in for an example. A stepped steel bar is suspended vertically. The diameter in the upper half portion is 10 mm, while the diameter in the lower half portion is 6 mm. What are the stresses due to sulfate in sections at B and A as shown in the figure? E value they have given, weight density rho that has been given. What is the change in length if E is given, if E is given twice, which is the same thing. Instead of 200 kilonewton per mm squared, it is 200,000 MPa. It is one and the same. Okay. First, what we will do it is we will find out stress at B. How do we find the stress at B? Stress at B will be due to weight of the portion of the bar BC. Whatever this weight is there, this would be contributing it to the stress at B. So, sectional area of BC we will find out, it is pi into 6 square divided by 4. Weight of the portion BC, that is W2 is equal to rho A2 L2. So, you know area, you know length, right, you know the unit weight. So, you can easily find out all these values. So, weight of the portion BC would be equal to 21.61 newtons. This weight will influence the stress at this particular point. So, stress at B would be equal to W2 divided by A2, which we will be getting it as 0.764 MPa. Now, stress at A, if you want to work it out, this is little bit tricky. This will be due to weight of the portion of the bar BC, this will be there, plus you will have weight of the portion of the bar AB. But look, weight of the portion of the bar BC, entire weight you can assume it to be acting like a concentrated load, and this is going to be distributed over its entire length. So, how we are going to do it? We will do sectional area of AB. This is A1, which is equal to 78.54 mm squared. Weight of the portion of the bar, weight of the portion of AB, if you work it out, it is rho into A1 into L1. Unit weight is given, area is known, length is known. So, you will be getting this weight as 60.04 newtons. So, stress at A, that is sigma C, W1 is what we have, W2 what we determined previously, W2 is 21.61, which will be acting throughout. When for the entire length, that weight would be acting. So, we will just add this 60.04 plus 21.61 divided by this area, that is 78.54, which we will get 1.04 MPe. So, the point that you have to notice in this stepped bar, in the portion BC, when you are going to consider, you consider only the self weight. Whereas, if you go to the portion AB and if you want to determine the stress at this point A, weight of the portion AB, which is going to be distributed from B to A, plus the entire weight, whatever that is acting, we will take in, you can consider it as a concentrated load. So, you can directly take W1 plus W2 divided by A2. So, these are the some small minor, what I should say, the tricks that you need to know, right, when solving such problems, or you need to have a broader understanding of the subject to see that how we are going to consider the forces separately for a stepped bar system. Now, we have to find out the change in length in the portion BC. See, for the portion BC, the change in length is mainly caused due to the weight of this portion. So, this is computed as W2 L2 divided by 2A2 into E. So, you can just find out this length. This is 00191 mm. Change in length in the portion AB, this is caused due to the weight of the portion AB and due to the weight of BC acting as a concentrated load at B, and this is computed as W1 into L1 by 2A1 into E plus W2 into L2 divided by A into A1. So, that means this is a concentrated load. This is due to self weight. This is self weight component. This is due to the concentrated load arising because of the self weight of the lower portion. That means this is equal to PL divided by A. So, please try to understand this. Here this is self weight. That is why we are having W1 L1 divided by 2A1 into E. This is a concentrated load, which is nothing but PL divided by A. So, we substitute these quantities and we will be getting the total extension as 0.0033 mm. Hence, the total change in length, first and the second we are going to add, and we are going to get it as 0.00521 mm. So, this is how we try to solve the stepped bar problem or the elongation that is arising because of the self weight of the bar. So, first we divide it into the lower portion, upper portion, lower portion we work it out separately, and to the upper portion separately plus contribution from the lower portion we add it and we try to work out this particular problem. Well, we have concentrated on several problems like extension of a tapering bar, circular in cross section, subjected to an axial load without considering the self weight. Next, extension of a rectangular bar subjected to an axial pull or an axial tension, again without considering the self weight. Now, how to find out the extension that are caused due to the self weight? Again, how we are going to do it in a straight bar or in a stepped bar. In a straight bar, we have done the derivation part of it, and through an example, I have tried to demonstrate how you can work out the change in length and the stresses in a stepped bar of varying cross section. Well, the next topic would be this important concept, what is called the Saint-Venant principle. See, what happens is, suppose you take a specimen like this and you apply a compressive force. We calculate the normal stress as force is equal to P divided by A, based on the assumption that the stress is going to be uniform across the entire cross section. But it so happens that uniform pattern of stress distribution will not be there in the immediate vicinity of the application of the load. Only if you move farther away from the load, that assumption of uniform stress pattern, right, will be nearly correct. For example, you take a specimen like this, and if you take 1/4, if you try to measure, or if you try to work out the strains and then you measure the strains, then from the strains you calculate the stresses based on the modulus of elasticity and other things. The strain readings based on which you are going to calculate the stresses will give you a stress pattern like this. Whereas we compute the stress as P divided by A, means this is where it is P divided by A. Now what happens is, immediately below the region of the concentrated load, the stresses will be more than the average load. Next, positions away from the load, means towards the ends, the stresses would be lesser than the average loads. Means the stress distribution is not uniform. Whereas if you move farther away, instead of, suppose this dimension is A, suppose you take 1/4, instead you take the entire distance, that as some A by 2 or whatever it is, whatever is this distance, you take this value as the A, you find the stress distribution to be very nearly uniform. That means the important point that you have to understand is, the assumption of uniform stress distribution due to the application of the load is not valid in the immediate neighborhood of the application of the load. In this region it will not be valid, again in this region it will not be valid. Away from this region, means somewhere in this particular region, if you try to work it out, the stresses would be equal to, the stresses will be fairly uniform. This is what was identified, and this has been put as Saint-Venant principle, and it says like this: at the point of application of load, the stress is distributed as shown in this particular figure, with stress being concentrated at the load point. Means, see, in this particular region the stresses are being concentrated. Away from this region, stresses decrease. The further the distance from the point of application of load, instead of this particular section, suppose I try to evaluate at this particular section, the stresses will be more or less uniform across the cross section. So this is what the Saint-Venant principle says. That means the assumption of uniform stress does not hold good in the immediate vicinity of the application of the load. Farther away from the load, your assumption of uniform stress and computing the stress as equal to P by A is nearly correct. So this is what is called the Saint-Venant principle. Because of this factor only, when you are performing the tension test, right, the ends of the specimens are provided with larger cross sections. Why? You can see that near the vicinity of the load, right, you will be having stresses more than the average value. So to see that specimens do not crush at those locations, they have more strength at the ends, so that they can resist this immediate shooting up, or what we call it as stress concentration effects. It can resist, but when you move further down, somewhere near the middle portion of the beam, middle portion of the specimen, the stress distribution will be more or less uniform. So we want the failure to take place because of a uniform stress prevailing over a region, not because of any stress concentration effects. Because of this principle only, that cross section of the specimen is being designed. This is a very important principle and strong application in mechanics and designs. We say that farther away from the load, all our assumptions are valid. Near the point of application of the load, definitely the values will shoot up. So therefore, when you are performing the designs, it is not just sufficient you design them for the average stresses, even for this local stress rising or local stress concentration effects should be taken into account. So these are some of the important concepts that we have considered so far in our discussions. Next we will go to the session what is called the compound or the composite bars. See, so far we have handled bars which are of varying cross sections. Some portion was circular, some portion was rectangular, and some in extension of a tapering bar of rectangular cross section or a circular bar, all that we have done. But throughout the modulus of elasticity, we have maintained it as same, means it is one material change in geometry. Now we are going to concentrate on that particular system, that is compound or the composite bars, wherein the geometry can also change, the material properties can also change. Means you may be having two different materials, three different materials having different moduli of elasticity. Such bars are called as compound bars or composite bars. See, a composite bar can be made of two bars of different materials rigidly fixed together so that both bars strain together under external load. Please look at this statement. A composite bar can be made of two bars of different materials, but they have to be rigidly fixed together so that both bars strain together under external load. Means if 1 mm is the deformation, both the bars should undergo 1 mm deformation, whether it is increase in length or decrease in length. Before I proceed further, please appreciate this point. A composite bar can be made of two bars of different materials rigidly fixed together so that both bars strain together under the external load. See, as the strain in the two bars are same, the stresses in the two bars will be different. Look at this nice situation. They deform by the same extent. If they deform by the same extent and if their lengths are same, then the strains will be same. Even though the strains are same, the stresses will be different because they are made up of what? Different materials. Because stress by strain is what? Modulus of elasticity. So therefore, as the strains in the two bars are same, the stresses in the two bars will be different and they depend on their respective modulus of elasticity. A stiffer bar will share major part of the external load. So this is some of the general concepts that we know, that we need to know about compound or composite bars. Number one, it is a bar which is made up of two different made of two bars of different materials. They have to be rigidly fixed together so that both bars strain together under external load. The strains will be same, but the stresses will be different because the modulus of elasticity different. And finally, a general conclusion is like a stiffer bar will share major part of the external load. Now, how do we find out the stresses in a composite bar? Look at this particular picture. We are having a hollow circular tube inside which we are having a solid one. This is a solid rod enclosed over in a hollow circular portion. The internal diameter of this, or the diameter of the solid shaft, is d and the outer diameter is d. The length is L. They are rigidly fixed together, right? And now if we are applying a force P like this, the bars, strictly speaking, will undergo, this one may undergo a deformation like this, the other bar may undergo a deformation like this, but overall both the bars elongate by the same extent, which we will call it as delta L. We know that both the bars will be strained together. So not that independently this can move by some amount, this can move by some amount. It is not possible. Both the bars simultaneously move to this particular extent, and that we will call it as delta L. So let us consider a composite bar consisting of a solid bar of diameter d, completely encased in a hollow tube of outer diameter d and inner diameter d, subjected to a tensile force P. Let the extension of the composite bar of length L be delta L. Common, like no change, like both the bars, that is, we will call it as a composite bar. The solid bar as well as the hollow tube will extend by an amount equal to delta L. Let ES and EH be the modulus of elasticity of solid bar and hollow tube respectively. Let sigma S and sigma H be the stresses developed in the solid bar and hollow tube respectively. The suffix S is for solid, the suffix H is for hollow. Now, since change in length of solid bar is equal to change in length of the hollow tube, we can establish the relation between the stresses in solid bar and hollow tube as follows. See, what is the condition that we are using? We are using the condition that change in length of the solid bar is equal to change in length of the hollow tube, because that is physically it is seen. If that is the case, then we can establish the ratio between the stresses in solid bar and hollow tube as follows. See, change in length, stress multiplied by length divided by modulus of elasticity. This is for the solid. Change in length for the hollow, sigma h, stress in the hollow bar, divided by modulus of elasticity of the hollow bar, and the length is the same. We use this as the condition. Change in length in solid bar is equal to change in length in the hollow tube. So, this transforms to sigma s is equal to sigma h into Es divided by Eh. Area of cross section of the hollow tube, you can quickly write it as Eh is equal to pi into d square minus d square divided by 4. Area of cross section of the solid bar, you can write it as As is equal to pi d square divided by 4. We know that the total load P is to be carried by the solid tube, by the solid rod as well as the hollow tube. So, we write P is equal to Ps plus Ph. Again I repeat, the suffix S is for the solid rod, the suffix H is for the hollow tube. So, load I will write it as stress multiplied by area, stress multiplied by area. So, now I have a relation between stress in the solid rod to the stress in the hollow tube, as sigma s is equal to sigma h Es divided by Eh. So, I will write P is equal to sigma h Es by Eh into As, that is I am trying to substitute for sigma s plus sigma h into Ah. I will put the entire equation in terms of sigma h. I will call it as sigma h plus Ah plus Es divided by Eh into As. So, this is the equation that we are going to have in the case of composite bars. Suppose the bar is not composite, the load is equal to stress multiplied by area. If it is composite, it is one common stress we will take and then multiplied by the respective areas Ah, Es. What is this particular quantity? Es divided by Ah. This is modulus of elasticity of the solid bar divided by modulus elasticity of the hollow tube. This is often called modular ratio because it is ratio of the modulus of elasticity of two different materials, and it is called the modular ratio. Well, sometimes in the problem what they can do it is they may not give you Es, they may not give you Eh, but they may directly say the modular ratio is 15. Then in that particular case what you need to take is you should not be confused that how we can solve this problem. Modulus of elasticity is not given, it may not be required, the ratio is directly given to you. So, Es by Eh is called the modular ratio. Using the above equation, the stresses in the hollow, you can find out what is the stress in the hollow tube. Suppose you know Ah, you know all these things, you know the load, I can find out what is the stress in the hollow tube. Once I know the stress in the hollow tube, I can find out what is the stress in the solid tube. So, like this we can solve problems not with just varying in geometry, they may be varying in geometry also, and they may be varying in material characteristics. You may have two different materials. Even in that particular case, the strength of materials will give you some elegant solutions. Maybe there could be some simplifications, some assumptions that are made and other things, but they are all good enough for fair degree of engineering accuracy. So, even such difficult problems wherein you are having two different materials can be solved based on one of the compatibility condition, that change in length of a solid bar is equal to the change in length of the hollow tube. We started from this and then we try to put everything in this particular form, then substituting for area of the hollow, area of the solid portion, load carrying capacities and other things, we have been able to get one equation as P is equal to sigma h Ah Es by H into Es. Particularly, please remember the ratio between the two modulus of elasticity, moduli of elasticity, that is Es and Eh, is called modular ratio. It may be, the values may be directly independently given, or it may so happen that they may directly give you the modulus of elasticity of the system is equal to 15. So, considering that, you should be in a position to solve these problems. So, how do we solve it? We use this particular equation. We try to find out stress in one material, then use this relation which will give you the stresses, the stress relation between two different materials. Once you know this, you can automatically find the value of the stress at the other point. Well, so far we have studied number of concepts like extensions of a tapering bar, circular cross sections, rectangular cross sections subjected to axial loads without considering the sulfate, next with considering the sulfate, and different types of problems, and also how to handle bars, composite bars or compound bars if they are made up of different geometry as well as different elastic properties. Mainly elastic properties means their modulus of elasticities will be different. In that particular case, how to develop those equations, what are the conditions that we are going to use, everything has been demonstrated. Well, I will stop at this stage. In my next class, I will be working out examples. Thank you.